Okay, so today we are just going to do some simple measurements, right, using a 1 mm cuvette here. Right, so the first thing is that before any measurements, we have to collect what we call the background reference. Right, so you have to see how your buffer actually affects lah. Right, a lot of buffers actually absorb. Right, so same thing I said just now, please use very clean tips. Autoclave tips, not clean, right? Because in SBS, people leave lots of junk in their autoclaves. Right, it's a lot of broth and everything else. Typical cuvette like this, right, takes about 100 200 microliters. Right, usually what you want to do is to have at least maybe about 1 centimeter plus, you know, of liquid lah. Right, just to get a signal, you know, because sometimes in this instrument itself, right, we can't see exactly where the laser is light source is going through, so you try to give enough, you know, so that it will be able to give you a signal. If you put too little, right, then you probably be getting, you know, just only the quartz. Yeah. So the Gansu Singaporean, right, will put 200 lah. Right, a few things, right, just for example first, I'll show you a few things first, please come over and see this, right. Maybe I don't even put buffer first. Right, AAPP, right, they also recommend actually doing what we call a pure air interface read. Only cuvette in air. Right, that is just for users to see whether the instrument is cranky or bad. Right, so this is how you see it. We just actually open this. Right, we will put this adapter inside here. Right, this adapter will sit in here.
How did you put it?
You can just take it up, just like this.
Okay.
Right. Right, and then you just have to slot the cuvette will go into here like that. So usually what we do is that we always leave the slanted part, right? The slanted part of the cuvette, right? Facing outwards, so that when the cuvette go in, right, it's such a easy guides it in. Right, don't put it the other way around. And always remember the direction. I always like the QS pointing towards the detector lah. QS. Right, this is nothing to do with the QS rankings of NTU. This is a QS course series of there. So I'm just gonna just put it in here, right, and then we'll close it. Right, and I'm just going to just do a simple acquisition at half a second. Right, 190 to that itself. I'm going to just click the other thing here. There's this SPEC thing here. This is one of the most primitive things that you can ever see lah. Click it once, right, and you see why. You have all the different ways you can rename the sample lah. So I just call it cuvette in air. Click OK, and then I'll just click the acquire button. Right, once you click acquire, right, the machine will, the software will scold you. No valid baseline available because you never do background lah. But I will just ignore that. I will just click OK. And then once that happens, right, in the background, the instrument will start running. Right, and you'll start collecting the CD signal from your this air interface. And many people, when they see this, right, they are very scared. Like, oh my god, why is it so spiky, so ugly? Like, people CD curve very smooth. But that's because the scale you see here is like, you know, 2 millidegrees, right? So it's a very narrow zone. Right, in actual fact, most of the CD signals you get, right, are in the tens or hundreds. So this is only like a 1% or less than 1% noise lah. But apart from that, right, in this CD instrument itself, right, we look at the CD signal itself. There's something else we can look for in this instrument here. When you right click, right, is look for what we call HV, high voltage. High voltage here, right, basically the detector here itself, right, runs up to 1000 volts. Which is based on the absorbance itself, right, it will actually raise the voltage, right, to kind of like collect the signal. And the maximum limit it can increase up to, right, is 1000 volts. So whenever you collect a CD signal, right, you find that the high voltage, right, is below 1000, your signals will be very good. But if let's say you collect a very bad curve, I can find some people's bad data later. I'll show you. Right, you can see that if towards some zones, right, the HV becomes 1000, right, actually the data not reliable. The machine clipping already ma. Right, so this is what we don't want to happen. Right, so if you go back to our CD plot itself, right, you will find that with CD plot, you find that great, you know, we are just only two units or so, right, and it's kind of like a pretty nice lah. And this data is in real time being saved into this file here. So anytime you say you accidentally close it, right, double click it, or it comes back up. Right. Now I will load buffer into this cuvette, and you will see what we see. But I have to say one thing, this buffer is about 4 years old or 5 years old. So whether it has grown any special organic materials inside, I don't know lah. But shouldn't have lah. SBS very clean, right? Our air is very good. Right, pipette, 200 microliters out. Close it. Right, this cuvette loading wise, put the tip right to the edge of the cuvette here, and just load it in. As you can see, 200 microliters, right, will give you something like a 1 inch, right? So same thing, QS rankings, the QS logo this way, right? Drop it in. Right, it's very easy to slide in. Later you go and feel for yourself, recognize everything, because when you feel the resistance, right, don't force it. You will hear that sound, right? That means it's broken inside, right? So same thing, we'll go back to our previous collecting software here, right? And then we just rename the file now, cuvette in buffer. It has an auto running number which is very irritating but I usually ignore the number, I don't care. I click it and just press acquire. Right, it's go you again. No valid baseline, but yeah, we actually collecting the baseline. That's what it is. Fingers crossed. 4 years or 5 years on the shelf in SBS. So a good buffer for CD itself, right, along the whole scale from 260 to 190 itself, right, it will not have very much of any signal contribution at all. Later I will go over, I will steal some PBS from somewhere. And you see the effect of just having NaCl. Oh, wonderful. So if you compare, right, how do you compare buffer to air, right? Click the file, drag it in. Great. Let me look at sample. Right.
This is PBS?
No.
Let's outside.
Oh, nice.
So, yeah.
Okay.
I try the faster setting. The fastest. Just click once. Then you see for yourself why we want to have a higher sampling time. Right. So this is 8 milliseconds. Let us do 0.5 seconds. So people ask us on the CD instrument itself, right? How many reads do we want to do? You need to read like 10 times or 20 times, or that. Actually, it's all averaged out in the duration of the scan. So the gray zone here, right? You see here, right? It's actually the averaging that is actually occurring. So the red line actually appears in the middle of the gray zone. So if you increase the time itself, right? Actually, it's already doing averaging on the during the acquisition itself. So you don't have to do too many repeats. Right, and we do one more time, 2 seconds. Slow. So you can see as it's running, right, the monochromator is actually also adjusting the wavelength in real time. Yeah. So a lot of people ask, what's the best time duration you should use on the instrument? Right, so I always tell them, I say, be patient. Right, if it's some experiment that you need to do once and for all, right, and not worry about it, right, 2 seconds a point, good data. Right, this instrument doesn't apply any smoothing. It's different from the instrument next door, Aviv Systems. There's a very nice CD instrument next door, RTP, and my good friend is actually the manager of that. Right, but the Aviv Systems instrument itself, right, gives very nice curves because in this software there's an auto smoothing function applied during acquisition. But for APP, the UK people, right, they're very proud of the system. They say APP is good, we don't smooth for curves. Connect it, you will smooth yourself later. So I'll show you how to smooth it. So over here, right, I'll just do a right click here right now. And you look at HV, high voltage. You find that at 0.1 mg per ml concentration for lysozyme, right, you can see the HV signal is within range. Later, I will just go up 10 times concentration. I will use 1 mg per ml and show you what happens. So when you do your CD next time, you see, hey, how come my signal always very bad, right? Over there, right? Please just look at HV. Right, maybe sometimes because the concentration is a bit too high. Right, then you just dilute it a bit, right? You get a signal you want. That's painfully slow. Okay, done. So let's go back to our curve. Right, see the curve. You see, this is at 2 seconds per point. This is at half a second a point, and this is at 8 milliseconds a point. Right. So I will suggest collect it at 2 seconds a point lah. But let's say, for example, over here, let's say I don't want some curves, right? Let me just remove it and close it first. I say I like the one that's from 2 seconds a point. Right, I want to present to my boss, but I haven't done my reference subtraction. How? You choose your keyword and buffer, drag it in, yeah, right, and then you just once inside here, right, press the D button. It's a D. Press it once. You can set your buffer as the baseline. Your lysozyme, right? Subtract baseline. Alright. Then this baseline itself, right, I can choose to unset it now, right? And the other two curves, I move out. And I just click OK. And this is the subtraction curve. Right. Apart from that, right, a lot of magic can be done on this instrument here. Like press D again. The curve is a bit not so smooth, right? right, you can actually select this. You can actually click the smooth function.
Okay.
Right, and usually window size for smoothing, right, try to be a few points only. 3 points, 4 points, 5 points, 6 points. That's all. Don't go to crazy smoothing because the algorithm, right, can convert an alpha helix into a beta sheet if you over smooth the data. This is actually very bad manipulation. So don't do that. Smooth it only when your original curve and the final smooth curve, right, overlap perfectly. Right, then you can justify smoothing lah. So you can see what happens if I do apply 4 points of smoothing, 5 points, 6 points, right? Maybe 4 points enough already. Right, as you click OK, right, residuals I don't need, I just remove the residuals. Right, you just click OK. You will see that the smooth curve is actually exactly overlapping your raw curve. You can present this. But what happens, right, if someone who is kind of like somebody who lacks data adjustment a lot, right? What can they do, right? They can actually do a lot of horrible things to the data, right? Imagine you apply something like 21 points of smoothing. Oops, did your just alpha helix become like a beta sheet, right? Yeah, you just converted it. So this itself is not legal, it's not legit, right? So don't use the smoothing function that way, right? Then sometimes your signals itself, right? Sometimes you find that my signal is a bit low. Maybe I got one mutant, right? The concentration is like cannot get very concentration, very little. Then my wild type is so much. Then on the CD itself, right? This your signal 很难看 right? It is actually okay to do normalization by multiplication. It's actually done with simple math lah. Click it once. Simple math. Multiply by how many times? So I say maybe by 10 times. Right, click OK. Right, and then you just click OK. And then you just readjust the scale. Your curve is now multiplied 10 times. So you just get it to the same dynamic range as your wild type. You can compare. Right, this is legit lah. Because the other way, if it's too dilute, right, use a longer path length lah. Right, 1 mm, 10 mm, you also 10 times one. Right, so it's the same, somewhat the same thing lah. Right, so these are all the basic manipulations that we roughly should do lah. Right, so far so good. All clear? Then now we just collect a concentration sample for you to see. Right, what happens if my sample is at 1 mg per ml?
This one is
0.1.
0.1.
So you can see I'm using the same sample, going up in concentration, right? So I don't have to wash my cuvette. But if you are going to do your other experiments, right? Let's say different samples, right? Then you have to use some buffer or some water to rinse your cuvette every time you do your experiment. Same thing, we just click this, which is 1 mg per ml. Okay, and acquire. One very important thing to take note also is that we collect our baseline buffer, right, separately, right? To do any mathematics, right, the collection parameters must always be the same. Right, what you mean by that, right, means that for example the wavelength you collect in the zone, right, and all that number of points, all that, right, must be exactly the same for buffer, exactly the same for sample. If let's say you collect different interval for sample and different interval for buffer, right, the software doesn't let you separate. Then you must export to Excel and do your rocket science. Most people are very happy to see signals that are so strong. But you can see that I did very conservative experiments here, so you can see that my buffer is total flatline. Right, so it's easy to get obvious data from the system. But if your buffer is not straight line, right, then of course you will have a bit of difficulties. going to look at HV. Right, it's going to clip already. Yes, it's going to keep going up. If you're super lucky, you will hit 1,000 lah. But most probably you will.
1,000 is
The limit of the instrument, and then it's also 1,000 volts going through here lah. So don't touch or adjust the connectors when it's running. See, it clip already. Right. So what happens when it clips, right? Actually, data is still being collected, right? But the quality itself is not going to be great. You can see that there's very little deviation here, right? But here it's getting noisy. Right, instead of a smooth curve, you get a spike. That's because you reach the instrument pressure limitation. Spiky, spiky. So it is simply can be solved by just dilution. Yeah, and you see this, how can you throw your boss? Boss will go through your window, right? Right, so you compare, right? Like they say, this concentration versus you know, is it 差得远? Right, so if you look on the HV clips. Right, so this is a simple way of troubleshooting the data. Yeah. Right now, I shall go and steal some PBS. Let me see what happens.